Hi everyone, we're going to be looking at Lewis acids and bases. Now, during the study, chemists have been collecting evidence and they have been doing experiments to find about the properties of acids and bases. Now, while they were doing so, they found that Bronsted-Lowry theory did not always hold true. So then the Lewis theory of acids and bases came to extend the understanding of acid and base reactions. So this is why we have different theories. So they have not been falsified, but they are extending each other. Okay, so we're going to be looking at the Lewis theory. Now, the Lewis theory talks in terms of transfer of electron pairs. So if you look at this example here, OH minus and H plus, we know that H plus acts as an acid and we know that OH minus acts as a base. But if you look at this reaction in terms of transfer of electrons, we see that the electron pair is being transferred from the OH to the H plus. From the OH minus to the H plus. So you have an electron pair transfer. So the OH minus is acting as an electron pair donor, while the acid is acting as an electron pair acceptor. And we're going to use that little arrow to show here that there is a donation of electrons from the OH minus. So this is called a dative bond that shows that there is transfer of electrons. So if you look at NH3 now, so NH3 and H plus, you can see here the NH3 is acting as an electron pair donor. So you have the formation of NH4 plus, and again here you can see the dative bond, which shows that it's the nitrogen that is giving the electron pair to the hydrogen. So we can define Lewis acids and bases. So a Lewis acid acts as an electron pair acceptor and a Lewis base acts as an electron pair donor. So we can have the H plus is a Lewis acid and the NH3 is a Lewis base. H plus is a Lewis acid and OH minus is a Lewis base. Now, this theory would enable many more substances to be classified as acids or bases compared to the Bronsted-Lowry theory. Now, Lewis acids, so Lewis pair acceptors, they are electron deficient, which means that they lack electron. If they lack electrons, means that they will be able to accept electrons. So they are able to add at least one extra pair of electrons. So example of Lewis acids we have. Now, transition metal ions can also act as Lewis acids. For example, Fe3 plus, Fe2 plus, they can act as Lewis acids when they combine with ligands to form complexes. Now, Lewis bases can be ions or they can be neutral compounds, but they should at least have one pair of non-bonding electrons, so one pair of lone electrons. So example, Cl minus, Pl minus, I minus, OH minus, Cl minus, NH3, and these are all ligands, and because they are ligands, they have one pair of they have one lone pair, at least one lone pair, hence all ligands are Lewis bases. Now, one thing to note that I already mentioned in class is that when you have curly arrows, the curly arrow shows the movement of electrons only. So a full arrow means a pair of electrons is moving, a half arrow shows only one electron is moving. And I already mentioned about the coordinate bond. For example, NH3, so you have the nitrogen giving the electron to hydrogen. So it is a covalent bond, but it is a special kind of covalent bond where the nitrogen is giving both electrons in that covalent bond. So let's see some example of reaction. So you have H plus and H2O. So here oxygen is going to donate an electron pair to H. So this is acting as a Lewis base. This is acting as a Lewis acid. So you have H3O plus, which is formed. Second reaction, BF3 and F minus. So here F minus is going to donate electrons, so it's an electron pair acceptor, Lewis acid, and F minus is a Lewis base. So you have the formation of BF4. So BF4 minus, and I'm showing the shape as well here. So this is trigonal planar and this is tetrahedral. Then you have AlCl3. These are little arrows, right? H3O plus here. And here what happens is that AlCl3 is going to form a dimer. So it dimerizes. Dimerizes means that two similar molecules are going to combine together. So Cl has lone pair of electrons, so it's going to donate it to aluminium. Aluminium has vacant orbitals. Here again, the Cl can donate to this aluminium. So you are going to have a dimer of AlCl3. So I'm drawing it like this. So the Cl gives to the Al and this Cl gives to the other Al. So this is how I'm going to draw this. So here you have the dimer of AlCl3. So Al2Cl6. Now iron here. So this is the H2O ligand. So it's going to combine with the transition metal ion. So you have 6 water that combines with this. So you have FeH2O 6 times. Here you have a complex ion which is formed, and here it's going to the Fe2 plus is going to act as a Lewis acid and the H2O acts as a Lewis base. So you have that complex ion which is formed here. Now last example where you have the formation of so BF3 NH3. So here you have the dative bonds. It's accepting electrons, so it is a Lewis acid. Here it's a Lewis base. Now we will stop here with the notes. I will mention something about nucleophiles and electrophiles. Now philes means liking. Nucleophile means that it likes the nucleus. So nucleus is positively charged. So something that likes positive charge. Electrophile, electrons are negatively charged. So an electrophile is a species that is attracted towards negative charges. So here nucleophiles are anything that have a negative charge or which has a region rich in negative charges, which is attracted towards nucleus or positively charged particles. And electrophiles, these are usually positively charged particles, and these are going to attract nucleophiles. Now, Lewis bases, they will be acting as nucleophiles because they are electron-rich species and they are going to be donating these electrons. So they have lots of electrons, they are electron-rich species, therefore Lewis bases act as nucleophiles. While positive charged particles, so they are electrophiles, so Lewis acids will be electrophiles. So with this, we end with this part for today's lesson.